In this video, we will explore our top 5 important concepts for hypothesis testing, including both 1 and 2 sample testing. Let's take a look at an example. The drug Eliquis is used to help prevent blood clots in certain patients. In clinical trials, among 5,924 patients treated with Eliquis, 153 developed the adverse reaction of nausea. Use a 0.05 significance level to test the claim that 3% of Eliquis users develop nausea. Does nausea appear to be a problematic reaction? Being that they asked us to test this claim, we want to start by setting up our hypothesis test. Most important piece is always that you do clearly label your null and alternative hypothesis. Our null hypothesis is going to be that the proportion is in fact 3%, with our alternative hypothesis being that the proportion is not equal to 3%. Other important information that they've provided us here is our significance level, 0.05, and then our sample size, of course, the number of patients with that adverse reaction, and p hat we have to find, which is x divided by n, which is approximately 0.026 if you work through that. We have our hypotheses. We still need to find our critical value if that's the approach that we wish to take, and we can do that using the calculator or, of course, the z-table. In the calculator, you're going to use your inverse norm function. Being that this is a two-tailed test, if alpha is 0.05, you have to split that in half. That's 0.025. Giving us our critical values of positive and negative 1.96. Don't forget that when you're dealing with two-tailed tests, it's always symmetric, positive and negative. Using the calculator, we can perform this hypothesis test, or of course you can do this by hand with the formulas if you choose to. This is a one sample proportion test, so a one proportion test rather, z-test. We're going to give it our population proportion, which is 0.03. And we have x over n. You have to adjust these if they're not still in there from the confidence interval top 5. And then select the appropriate test that you're doing, which is two-tailed. This gives us a z-test statistic of negative 1.882 or 883. At this stage, you can use your test statistic and critical values, or if you wish, you can use your p-value, which our p-value is equal to 0.0597 or just 0.6. And that's given right here. Do not confuse p hat with our p-value. Those are two separate things. Now, depending on which approach you take, they both tell us the same thing. In this case, we have critical values of negative 1.96 and positive 1.96. And our test statistic fits right over here. Our test statistic does not land in the rejection region, so we say that we fail to reject our null hypothesis. What does this mean for us? There's insufficient evidence to reject the claim that 3% of Eliquis users develop nausea. Why is this, or is this problematic? This would not be really problematic because 3% is a relatively low percentage. So does nausea appear to be a problematic reaction? Not really, because 3% is a very small proportion for people to be affected by. If in fact the percent was much higher, it would be a lot more statistically significant and make for a bad reaction, a bad side effect, if you will, of this drug. Let's look at another example. Students were asked to estimate the length of 1 minute without reference to a watch or a clock, and the time in seconds are listed below. Use a 5% significance level to test the claim that these times are different from the mean, which is expected to be 60 seconds. Does it appear that students are reasonably good at estimating 1 minute? first thing you want to do here is go ahead and enter all of this data into your stat menu. So we've already entered our data here. And then you can go about listing out your findings if you want your mean and standard deviation, etc. If the data is already entered and you're not given something like a proportion test like we had before, then you can jump straight into your hypothesis test once you've set up your null and alternative hypotheses. We want to test the claim that these times are from a population with a mean equal to 60 seconds. So we're testing, is that mean actually 60 seconds? And our alternative is that they were not successful in doing so. Okay. For this, we're going to use our t-test function. We have our data entered, so tell it where you put that information. This is a mean of 60. That's where you enter your population mean, what you're testing against. And we get a t-test value of 0.530 with a p-value equal to 0.604. So whichever technique you prefer using, whether it's p-value or otherwise, this is where you would make your decision. If you want to use the test statistic method, we have to find a critical value, and we can do that using the t-inverse, which is option 4 here. Area to the left, if this is 5%, that's 0.025. We have a total of 15 pieces of data, so that means we have 14 degrees of freedom, which gives us a t-critical value of negative 2.145. However, being that this is two-tailed, it's positive and negative 2.145. We can see that our test statistic is nowhere close to our critical value, which we run into the same issue we had before. We fail to reject our null hypothesis, which is not necessarily a bad thing. In this case, we were looking to see how close students were able to estimate to that actual 60-second mark. Because we fail to reject our null hypothesis, it does in fact imply that students are getting pretty darn close to that 60-second mark. So does it appear that they're reasonably good at estimating 1 minute? Although we had a couple of students in here, like the 21 seconds and then these 90 seconds over here, who were extremely low in their estimate or extremely high in their estimate, the rest of them did seem to be relatively ballpark or close enough, so to speak. So are students doing a good job at estimating? Sure, they're doing a great job at estimating here. We don't have enough evidence to conclude anything other than that. For our next example, let's look at what happens when we start having two samples of information. A study of seatbelt use involved children who were hospitalized after motor vehicle crashes. For a group of 123 children who were wearing seatbelts, the number of days in the ICU has a mean of 0.83 with a standard deviation of 1.77. For a group of 290 children who were not wearing their seatbelts, the number of days spent in an ICU has a mean of 1.39 with a standard deviation of 3.06. At a 5% significance level, test the claim that children wearing seatbelts have a lower mean length of time in the ICU than for those children who were not wearing their seatbelts. So before we begin, it does help if you take a moment and organize all of your data. First thing, we know that from our first sample, we'll call this N1, the size was 123 children, and these were the children who were wearing their seatbelts. We had a mean in that sample of 0.83 with a standard deviation of 1.77. For the children who were not wearing their seatbelts, we had 290 with a mean of 1.39 and a standard deviation of 3.06. So I'm using the subscripts here just to help alleviate any confusion so we don't mix those two things up. We want to know, we're testing the claim here, if children wearing their seatbelts have a lower mean length of time in an ICU than those who did not. So in other words, we want to see if the mean of our children with seatbelts is lower than this mean over here. Do we have enough evidence to conclude that? Our null hypothesis is that those two are in fact the same amount of time. Our alternative, this is what we're investigating, is that the mean of the first is actually lower or less than the mean of the second. Being that we have two sets of information, and these are independent, what makes them independent? The fact that these are children, right? The sample are children who were wearing seatbelts. This is the sample that they were not wearing seatbelts, so they have no interaction with each other. We're going to use a two-sample t-test, which is our fourth option here. Being that we have data already compiled, we're not going to use the data setup, we're going to use the stat setup. We need to enter that information. We have a mean of 0.83 for the first with a standard deviation of 1.77. Enter your sample size here. Same thing, mean of 1.39 with a standard deviation of 3.06 and a sample size of 290. Below that, we have to adjust what are we looking for when the mean is less than. So we're going to use the second option here. This data is not pooled. And then you're going to calculate. So this readout gives us quite a bit of information. Okay. You'll notice our t-test statistic and our p-value. With a p-value of about 0.01, if you compare that to our significance level of 0.05, we can say that we reject our null hypothesis, which for us, that does in fact mean that we have sufficient evidence which supports the fact that the children who wear their seatbelts spend less time in the ICU than the children who do not wear their seatbelts. So if there is a crash, then they're spending less time in the ICU than those who are not wearing their seatbelts. And in this case, that's a positive thing. It means that seatbelts are in fact helping for whatever injuries they might be receiving in those accidents. Researchers from the University of British Columbia conducted a study to investigate the effects of color on cognitive tasks. Words were displayed on a computer screen with background colors of red and blue. Results from the scores on this test of word recall are given below. A higher score corresponds to greater word recall. Using a 0.05 significance level, test the claim that the samples are from populations with the same mean. Does the background color appear to have an effect on word recall scores? If so, which color appears to be associated with the higher word memory recall scores? So similar to what we saw before, we have two sets of data. We have those with a red background, those with a blue background. These are independent because someone's going to see one or they're going to see one or the other, but not at the same time. Set up our null and alternative hypothesis, or hypotheses. We want to know, does the mean of the red background equal the mean of the blue background? And we're testing to see if those are in fact the same. So the alternative is that they are not in fact the same. Okay, red and blue, red and blue. For this, we would use the same two-sample t-test function. Just change the information that we have. The mean of the first is 15.89 with a standard deviation of 5.9. Mean of the second is 12.31 with a standard deviation of 5.48. And this time we're checking to see, are they equal, not equal? Information is not pooled, so we have the results of our t-test here. Our p-value is 0.0101, which is smaller than our significance level of 0.05. Or if you prefer, you could use the test statistic functions and then find the critical value. So in this case, we see that we reject the null hypothesis. P-value is smaller than alpha, which means that we do have sufficient evidence to conclude that the means are in fact different, which if the means are different, it implies that one of those colors has a higher word recall rate than the other color does. So now, if you were trying to figure out which color might be higher, take a look at the data, take a look at what it says. The red background has a higher mean, and the standard deviation is just a little bit larger, but not substantially different than that of our blue background. So it seems to be that the red background provides a better memory recall or a higher word memory recall according to this information. One more example we're going to look at is now dealing with two samples where we no longer have independent data. Listed below are the heights in inches of mothers and their first daughters. The data are from a journal kept by Francis Galton. We use a 0.05 significance level to test the claim that there is no difference in heights between mothers and their first daughters. What makes this data dependent as opposed to independent? When you're dealing with mothers and children, there is a genetic factor involved in height. So, being that they are paired, mother-daughter, we have to be careful and recognize that there is potentially an effect based on the height of the mother versus the height of the daughter. So what we're going to do is test the differences. In other words, they're asking us test that there is no difference. Okay? When you see that and you recognize that this data is dependent, you're going to take a moment and calculate all of the differences. To do this, you can do so very quickly by using your stat function actually. Clear out whatever's there and enter the data across in list 1 and then enter the second set of data in list 2. Once you have your data entered, you're going to use the next list to subtract those two. We can do this by telling it to take list 1 and subtract list 2. And this deals with all of those differences for us. I'm going to take a moment and copy that over. Being that this data is no longer independent and we're testing the differences, you can use a regular old t-test for something like this. Before that, you need to make sure that you set up your null and alternative hypotheses. Our null hypothesis being that the mean of the differences is 0, which would imply that there's no difference in their height, or test the alternative that the mean is not equal to 0. So go into our test functions, and you're going to set up your t-test. Tell it to take the data that we have. In this case, we want the mean to be 0. And our list that we're using is the list of differences, which is list 3. Here we get a t-test value of negative 1.379 and a p-value of 0.201, which means that we fail to reject our null hypothesis, which supports what we were testing. We fail to reject our null hypothesis, which implies that we have insufficient evidence that the mean difference in height is anything other than 0. So it means, in fact, that we've shown there is evidence supporting that there's no difference in the height of mothers and their first daughters. Thank you for watching.